agree the recording, and we also have some audience could not come in today, but they would like to watch it on YouTube to learn about the research frontier. Good morning, good afternoon, good evening, everybody. Welcome to the Secure Data webinar. It is our great pleasure to have Dr. Damanveer Grewal speaking with us from Caltech. So Daman got his degrees in India in IIT before he moved to Rice University for his PhD. And he has been working on experimental petrology, especially on the life essential volatiles in the early process. So in this talk, he's going to talk about his work that's especially he conducted in the recent years and expanded far beyond the Earth to the other rocky planets in the inner solar system. So with that, Daman, it's your time. And normally our talk goes for 40-45 minutes, but it's a little bit relaxed because web version, and we leave some time for interaction with our participants. So please, Daman.
All right, thank you. Thanks for the invitation. And I'll try to go really slow. And if you have any questions, you can interrupt me or put them in the chat. I'll try to answer as soon as I look at them. So basically in this talk, in this presentation, I'm primarily going to talk about the origin of three key life essential volatiles in the rocky bodies of the inner solar system. And those three volatiles are primarily nitrogen, carbon, and water. And in this talk, I'm primarily going to focus on nitrogen and carbon. I've been doing work on water recently, but that's for some another day. So this work that I'm going to present today combines many different aspects of meteoritics, high pressure temperature experiments, isotope geochemistry, to shed some very new perspectives, some very fresh perspectives on these very important problems. So first of all, why are we interested in this particular problem? We know that Earth is the only habitable planet that we know of in our solar system and beyond. In addition to the presence of sufficient liquid water, the composition of Earth's atmosphere, primarily composed of elements like nitrogen and carbon, plays a critical role in defining the habitability of a planet. Also, we know that nitrogen and carbon, along with other volatiles, are the primary components of the basic building blocks of life on a planet. If we are interested in understanding the habitability of our planet, we need to understand the origin of these volatiles in the Earth's atmosphere. But if you look at the present-day Earth's atmosphere, it's a dynamic parameter which keeps on changing over billions of years of Earth's history due to exchange of volatiles between the Earth's interior and superficial reservoirs. Therefore, if you want to understand the origin of volatiles, these life-essential volatiles in the Earth's atmosphere, we need to track the origin of these volatiles in this big box over here termed as the bulk silicate Earth. Because over billions of years of Earth's history, the exchange of volatiles between the Earth's mantle, the crust, and the superficial reservoirs, including the atmosphere, controls the composition of the Earth's atmosphere. The origin of volatiles in the bulk silicate Earth is generally tracked by comparing the isotopic composition of the volatiles in the bulk silicate Earth, represented by this red star over here, with different cosmochemical reservoirs. When people do mixing calculations, we have understood that the nebular gas and the cometary reservoirs do not contribute significantly to the volatile budget of the bulk silicate Earth. But then when we plot different classes of chondrites over here, so chondrites are remnants of primitive planetesimals in the early solar system. They're very primitive materials. And we plot nitrogen and carbon isotopic compositions of different classes of chondrites over here. They're very similar to that of the bulk silicate Earth. So our general understanding is that the volatiles in the bulk silicate Earth and these chondrite-parent bodies had common origins. But if we compare the abundances of these volatiles in the bulk silicate Earth relative to primitive chondrites, we see that the bulk silicate Earth is extremely depleted in these volatiles by 2 or 3 orders of magnitude relative to these primitive chondrites. So we have two contrasting observations over here. On one hand, we see this isotopic similarity of the volatiles in the bulk silicate Earth and chondrite parent bodies. But on the other hand, we see that the bulk silicate Earth is extremely depleted on this. The volatiles are very depleted in the bulk silicate Earth. So the idea is, how do you put all of these observations kind of together? If you look at chondrites, they are very complex assemblages composed of many different phases. They have calcium aluminum rich inclusions, chondrules, and metal. They are high temperature phases. And most of the volatiles are actually located in the matrix of these chondrites, which is these low temperature aggregates which hold the whole chondrite assemblages together. But if you look at a differentiated planet, for example, Earth, we know it's a differentiated body and it does not look anything like that of a chondrite. So if you want to track the origin of volatiles in rocky planets, we need to track the journey of volatiles from chondrite-like assemblages to differentiated rocky bodies which have crust, mantles, and cores. To track this journey, I have represented this entire journey by a very simple schematic over here, where you start with initially gas and dust in the solar nebula. The dust particles clump together to form the first planetesimals. And these planetesimals, if they form very early, they undergo melting due to the inheritance of short-lived radioactive nuclides like 26 aluminum, which start to decay and lead to melting of these planetesimals. So you form differentiated planetesimals with cores and mantles. Then these differentiated planetesimals collide amongst themselves to form larger planetary embryos. And subsequently, these planetary embryos collide amongst themselves to form large Earth-like planets. What I'm going to try to convince you in this particular talk is that all the interesting processes related to the origin of volatiles in the bulk silicate Earth or the rocky planets of our solar system, related to the budget of volatiles in the rocky planets, actually takes place very early in the solar system history. That is during the formation and differentiation of these planetesimals. All the interesting processes take place in these very small bodies. So basically, I'll try to guide you through my ideas by asking three particular questions. So the first question I'm going to ask you, do chondrites, these primitive materials, do they actually capture the volatile inventories of the earliest formed planetesimals? Do chondrites actually capture the bulk inventories of these earliest planetesimals? And I'll try to convince you they actually do not. I'll give you this answer right now. And so basically, I'll use another class of meteorites, that is iron meteorites. And using high pressure temperature experiments, I'll ask questions and try to answer, what do isotopes of volatiles in iron meteorites tell us about the origin of volatiles in the Earth? And can iron meteorites, rather than chondrites, explain the unique volatile depletion pattern of the Earth? So to answer the first question, let us look at our current understanding of the initial architecture of our solar system. Based on nucleosynthetic anomalies of several non-volatile elements, we know that rocky materials in our solar system come from two different reservoirs. Carbonaceous chondrites, which are generally more volatile rich, they come from the outer part of the solar system. And meteorites like ansatite chondrites and ordinary chondrites, the inner solar system meteorites, they come from the inner part of the solar system, sampled over here. It's very important to look over here is that ansatite chondrites plotted over here are isotopically very similar to that of the Earth. So they are very special kind of chondrites, and they're very similar to Earth and other rocky planets in our solar system, including Mars. The interesting thing about these early accreting planetesimals is that they accrete so early, they inherit a very important short-lived radioactive nuclide, that is 26 aluminum. 26 aluminum has a half-life of 0.7 million years. So planetesimals that accrete within the first couple of million years of solar system formation, they should inherit a lot of 26 aluminum, which should cause a lot of melting and differentiation in these bodies. This process can be represented by this simple schematic over here. That is, you start with a planetesimal that accretes very early. It inherits a lot of 26 aluminum. Due to the decay of 26 aluminum, the planetesimal starts to melt. So basically, you have a thermal boundary layer on the top, which does not undergo melting. And beneath this thermal boundary layer, you have planetesimal that undergoes differentiation. The metallic melts eventually start to separate from the silicate melt to form the metallic core. So you basically gradually start to heat up a planetesimal, and eventually, as the planetesimal reaches very high temperatures, the planetesimal undergoes core mantle differentiation. And eventually, a differentiated planetesimal would look something like this. You would have a primitive crust on the top, which does not undergo melting. But it's interesting to note over here, the surface of these planetesimals would be very cold. And as you go underneath these chondritic layers or these primitive layers, you go to higher and higher temperatures. So this would be a map of thermal metamorphism in these planetesimals. So basically, a point closest to the surface would experience very low temperatures, and a point deeper in the superficial layers would experience higher temperatures. So it would be a map of thermal metamorphism. You go deeper into the layers, you experience higher thermal metamorphism. And eventually, underneath these undifferentiated layers, you would have a magma ocean, a differentiated mantle, and eventually you would have a metallic core. So remember this architecture. You have differentiated planetesimal with a primitive crust. As you go deeper into the primitive crust, you are thermally metamorphosed or higher temperatures, and then you have a mantle and a core. So this is a current understanding of the architecture of of uh, of early forming planetesimals. And chondrites actually only sample the surfacial layers of these planetesimals. They do not come from anywhere else, only the superficial layers. So what about the volatile inventories? The question I asked was, do chondrites actually capture the inventories of the entire planetesimals? To answer this question, over here, I have plotted the nitrogen contents in bulk chondrites as a function of their peak metamorphic temperatures. So peak metamorphic temperature, again, would be as you go deeper into these layers, the peak metamorphic temperature keeps on increasing. So the most primitive layers have high amount of nitrogen, and as you go deeper and deeper, the nitrogen contents begin to drop off, which simply tells us that as the metamorphism keeps on increasing, as you keep on increasing temperature, you keep on losing nitrogen. The nitrogen inventory keeps on decreasing. And what you can understand from this particular plot is that chondrites that come from over here, they do not tell us anything about the nitrogen inventory within the entire planetesimal. And the similar story holds if you look at the nitrogen isotopic compositions as well. The chondrites which come from the superficial layers, they are very 15 enriched. Their delta 15N values are high. And as you go to deeper and deeper layers, the nitrogen isotopic composition also begins to drop off. So what you're seeing over here is you're losing 15 enriched components as the temperature keeps on increasing. So what this kind of tells us is that these superficial layers or the chondrites do not tell us anything about the bulk volatile abundances and the isotopic compositions of the earliest formed planetesimals. They only tell us about the superficial layers. And even within these superficial layers, you have to keep track on the grade of thermal metamorphism. But these superficial layers are actually very thin. So the current idea is that the chondrites may actually not capture the bulk volatile abundances and the isotopic compositions of the earliest forming planetesimals. If this is correct, how do we move forward now? So basically, what we are going to use in this particular talk is another class of meteorites that's very critical, and those class of meteorites are iron meteorites. So first of all, what are iron meteorites? So iron meteorites are the remnants of the metallic cores of the first formed planetesimals in the solar system. If you look at their accretion ages are right at the onset of the solar system formation. And we know from planet formation models that the seeds of the rocky planets started to form very, very early. So it is very possible that iron meteorite parent bodies actually are more representative of the seeds of the present-day rocky planets of our solar system. So how are iron meteorites formed? So in iron meteorites, again, when you heat up a planetesimal, the planetesimal undergoes magma ocean-like conditions. The metallic droplets start to separate out from the silicate melts to form the metallic core. And before separating from the silicate melt from the magma ocean, they undergo equilibration between the metallic and silicate melts. So if you keep track, if you sample the metallic core, and if you know the exchange or the equilibration exchange coefficient between the magma ocean and the metal, you can actually track the composition of the entire planetesimal. So basically, we're gonna use iron meteorites now. And we are more interested in iron meteorites that come from the inner part of the solar system, because as we saw earlier, that most of the rocky planets including Earth, as I showed in this particular plot, they are mostly made up of inner solar system planetesimals. The contribution of outer solar system planetesimals is very limited. So what we need to do over here is track the volatile abundances of these planetesimals, if these earliest forming inner solar system planetesimals. The general idea is, when people do astrophysical models, the general idea in those astrophysical models is that the inner part of the protoplanetary disk should be extremely hot during the early stages of solar system formation. So what people expect is that you cannot condense volatiles in the inner part of the disk. So people generally believe that the earliest forming planetesimals in the inner part of the solar system should be extremely volatile poor or almost volatile free, that should not contain any volatiles. But now so if this is true, if the bulk planetesimals should be volatile free, it means their cores should be completely volatile free as well. But when I started looking into the literature data for different classes of iron meteorites over here, the story is completely different. Over here, you see the carbon and nitrogen contents of iron meteorites. The red color symbols represents iron meteorites that come from the inner part of the solar system, and blue colors represent the outer part of the solar system. And what you see in this plot over here is that the inner solar system iron meteorites, they contain a bunch of carbon and nitrogen. And in some cases, it's interesting to know that the inner solar system iron meteorites, the 1Cs and the 1AB groups, they're actually the most volatile rich iron meteorites, or they sample the most volatile rich cores. Each body over here, each group over here represents a distinct parent body. So this shows us that the inner solar system, the inner solar system iron meteorites that contain nitrogen and carbon, which means that parent cores also contain nitrogen and carbon. What I showed a couple of years ago is that if you look at the inner solar system iron meteorites, the nitrogen isotopic composition is also distinct relative to the outer solar system iron meteorites. So what this tells us is that the inner solar system iron meteorites, they not only contain nitrogen, but their nitrogen is isotopically distinct relative to the outer solar system reservoir. So what this kind of tells us is that the inner solar system iron meteorites inherited nitrogen, or the inner solar system cores also inherited nitrogen as well as carbon. So what do the nitrogen isotopic signatures of iron meteorites tell us about the origin of volatiles in the Earth? If you look at the nitrogen isotopic composition of the Earth's mantle, it is actually very similar to that of ansatite chondrites. So a general understanding is that if the ansatite chondrites are the basic building blocks of ansatite chondrite-like materials are the basic building blocks of our planet, and if the isotopic composition of nitrogen isotopic composition of ansatite chondrites is very similar to that of the Earth's mantle, so it kind of tells us that most of the nitrogen in the Earth's mantle was sourced from the inner solar system reservoir. But if you look at the nitrogen isotopic composition of these inner solar system iron meteorites, they plot in a much wider range. The nitrogen isotopic compositions are actually much more negative than that of ansatite chondrites. So the next question arises, what does this actually mean? So what do nitrogen isotopes in iron meteorites tell us about the origins of volatiles in the Earth? So to answer this question, let us again look at how these iron meteorites are formed. So what we have right now is the nitrogen isotopic signatures of iron meteorites. What we are interested in is the nitrogen isotopic composition of the bulk planetesimal. We know these iron meteorites were formed during core mantle differentiation, and during this core mantle differentiation in this magma ocean stage, the metallic droplets actually equilibrated with the silicate melt. So if we could somehow experimentally constrain the equilibrium isotopic fractionation factor of nitrogen between the metallic and silicate melts, we know the nitrogen isotopic composition of the parent cores from iron meteorites, we can actually constrain the nitrogen isotopic composition of the bulk planetesimal, because we know the nitrogen isotopic composition of the alloy. We know if we can somehow constrain the nitrogen isotopic fractionation factor, we can actually calculate the nitrogen isotopic composition of the silicate melt. And if we know nitrogen isotopic composition of the silicate melt of the metallic melt, then we know the nitrogen isotopic composition of the bulk planetesimal. So there has been a study a few years ago, they actually constrained this particular number. What they showed in that particular study is that the gap delta 59 value, this isotopic fractionation factor, is actually a strong function of oxygen fugacity. And what they showed over here is that this gap delta 59 values are actually very large. These numbers are very, very large, around 200 to 200, as large as 250 parts per mil. And if these numbers are correct, then the nitrogen isotopic fractionation during core mantle equilibration should be very large. So what does it actually mean? So what this means is, so if this gap delta 59 value is large as well as negative, so what this means is during core mantle differentiation, if you start with ansatite chondrite-like materials, then core mantle differentiation should push the nitrogen isotopic signature of the alloys of the metallic cores towards more negative values. So what this means over here is that if these numbers are correct, then you could start simply with an ansatite chondrite-like bulk material composition, and during core mantle differentiation, the nitrogen isotopic signatures of the metals are pushed towards more negative values. But there are extreme problems with this, extreme theoretical problems. Because if we look at theoretical calculations, we do not expect the nitrogen isotopic fractionation or any kind of isotopic fractionation between two systems at very high temperatures to be that large. To understand whether these values are correct or are reliable, we need to look at how these values are determined during high pressure temperature experiments. So what you do in high pressure temperature experiments is you take up metallic and silicate powders, you put them inside a capsule over here. Generally, people do these experiments in a graphite capsule and put these capsules under very high pressure temperature experiments. Then what people do is, after the experiment is done, they take up the products and measure the total nitrogen contents in the final products and compare them to the starting materials. And what people have seen over the years is that there is a loss of nitrogen from the capsule during the experiments. That is, if you constrain the total amount of nitrogen in the alloy and silicate melts in the products and compare them relative to the starting materials, you have lost some nitrogen. So if the nitrogen is lost, but it is stored in the porosity of the capsule walls, which means then this whole capsule, that is the capsule material, including the sample, this should act as a closed system. And the nitrogen isotopic fractionation that you're measuring between the metals and silicates, it should be close to equilibrium nitrogen isotopic fractionation. But if you have a nitrogen loss across the capsule walls, then the nitrogen isotopic fractionation should be affected by kinetic values. And I want you to remind over here, what we are interested is in equilibrium nitrogen isotopic fractionation, because we believe when the metallic droplets are separating out from the silicate melts, they are in equilibrium with the metallic droplets are in equilibrium with the silicate melts. So what you actually need is equilibrium nitrogen isotopic fractionation rather than kinetic nitrogen isotopic fractionation. And if you look at the data of the previous study, if you plot the delta 15 and silicate values as a function of the fraction of nitrogen remaining, you see classic trends of kinetic isotopic fractionation. That is, as you lose nitrogen from the system, your nitrogen isotopic signature in the silicate melt keeps on getting higher. So what this means over here is the nitrogen isotopic fractionation measured in that particular study were actually affected by kinetic processes, but we are interested in equilibrium nitrogen isotopic fractionation. To understand, to actually constrain the equilibrium nitrogen isotopic fractionation, I have done a lot of experiments over the last few years. And what we did in this particular experiments, we did a bunch of experiments in graphite capsules in relatively low pressures and temperatures relevant for differentiation in planetesimals. And then we did different sets of experiments, time series experiments, and so on and so forth. And these experiments were also calibrated with some ab initio calculations. So this is a typical experimental product that we have. So you have an alloy melt, which is an analog of the metallic core. You have a silicate melt, which is an analog of the magma ocean. You separate out from the metals and silicates and measure their isotopic compositions of both the metals and silicates by an elemental analyzer with very good analytical precision. So over the next 5 or 10 minutes, I'll go into the details of the experimental results, and then I'll come back to the main story. Like, can we use the nitrogen isotopic composition of iron meteorites to reconstruct the nitrogen isotopic composition of the bulk planetesimals? So what do our experimental results show over here? So if you look at the time series experiments, so each symbol represents a given time series over here. So if you look at the percentage of nitrogen retained in our experimental products as a function of time, you see that the percentage of nitrogen retained as a function of time does not change. So which means is that we are not continuously losing nitrogen from the capsule as a function of time. And if you look at the nitrogen isotopic composition of both the metals and silicates, they also do not change as a function of time. The shortest experiment also have similar nitrogen isotopic composition of the metal and silicate, and as in comparison to the longest possible experiment. So these experiments are done under exactly the same pressure, temperature, and chemical compositions. So basically, you see the values do not change. So which kind of tells us that the nitrogen isotopic fractionation that we are actually measuring in our experiments is not kinetic isotopic fractionation. It is actually close to equilibrium nitrogen isotopic fractionation. And also, it's important to see over here, as in comparison to previous study, the metal is again similarly lighter than the silicate melt. And if we compare our cap delta 59 values right now, the nitrogen isotopic difference between the metallic and silicate melts is very low, around -1 to -2 parts per mil. And if you compare the results of the previous study, it was as high as -250 or -300 or 300 parts per mil. And then we did a bunch of other experiments over different sets of conditions, and the results were exactly the same. The nitrogen isotopic fractionation between the metals and silicates is very limited. Metal is lighter, but not by that much. So then if we collect all the data from our experimental results and put them together and plot it across oxygen fugacity scale, we see that the nitrogen isotopic fractionation between metal and silicate melts is a function of oxygen fugacity, but the magnitude of nitrogen isotopic fractionation is very limited, around -1 to -2 parts per mil. And if we compare these results to the previous study, they're very, very different. And another important thing to note over here, not only the magnitude is different, but if you look at the trend of cap delta 59 values as a function of oxygen fugacity, it's completely different. So how do you agree? How do I convince you that actually these new experimental results are more representative of equilibrium nitrogen isotopic fractionation between metal and silicate melts? To convince ourselves, we started to do ab initio calculations. So ab initio calculations are completely unaware of our experimental results. So what we do in our ab initio calculations is, what we did in our ab initio calculations is can we recreate both the magnitude as well as this trend of nitrogen isotopic fractionation between metal and silicate melts using these ab initio calculations. So what we know from previous experimental studies is that the nitrogen speciation in the metallic melts does not change as a function of oxygen fugacity. So this fractionation between this trend of nitrogen isotopic fractionation does not depend on the nitrogen isotopic composition of the metallic melts. But if you look at the nitrogen speciation in the silicate melts, it actually changes as a function of oxygen fugacity. That is, if you are at more oxidized conditions, nitrogen in the silicate melts dissolves in the form of N2 somewhere over here. And as you go to more and more reduced conditions, nitrogen dissolves in the silicate melts in the form of N3 negative. So you look at nitrogen oxidation state 0, at more reducing conditions, it's -3. But in experimental studies, there is also hydrogen. So basically, the gradual nitrogen speciation change as a function of oxygen fugacity as you go to more and more reducing conditions takes place from nitrogen to NH3 to primary amines to secondary amines and finally to tertiary amines. So what we did in this numerical ab initio calculations was we actually calculated the equilibrium fractionation factors of all these species as a function of temperature. And these temperatures are relevant for experimental results. So what we see in these ab initio calculations are that the metal is lighter, the nitrogen isotopic signature of metals is lighter than that of the silicates, which is completely in agreement with our experimental results. And then we subtracted the nitrogen isotopic composition of the silicate melt from the metallic melt to convert this y-axis to a similar kind of a plot. And when we do that, we see that the nitrogen isotopic difference between the metallic and silicate melts as a function of oxygen fugacity is almost identical to our experimental results. At more oxidizing conditions, the nitrogen isotopic fractionation is around -3 parts per mil, as you see over here, and the magnitude keeps on decreasing as you go to more and more reducing conditions, and the numbers are around -1 parts per mil. So basically, this shows us the power of combining experimental results with TFT calculations and try to convince ourselves that whatever experiment, these equilibrium isotopic fractionation factors that we calculated by experimental results are truly representative of equilibrium nitrogen isotopic fractionation between metallic and silicate melts during core metal differentiation. So to go away from the experimental results, let's just remember one part, that the magnitude of nitrogen isotopic fractionation between the metallic and silicate melts is very limited. Now let's come back to the main story. We know from the iron meteorites the nitrogen isotopic composition of the metallic melts. Now we have constrained the equilibrium nitrogen isotopic fractionation factor between metallic and silicate melts. Once we now know this, we can actually calculate the nitrogen isotopic composition of the silicate melt. And when we know this, we can reconstruct the nitrogen isotopic composition of the bulk planetesimal. And what our calculations show over here is, for all different planetesimals that are plotted over here, the nitrogen isotopic composition of the iron meteorites, which sample the parent cores, are actually very representative of their parent bodies. The nitrogen isotopic composition of the bulk planetesimals are actually very similar to that of iron meteorites. So what this means over here is that these iron meteorites, they actually capture the variation of nitrogen isotopic composition of the inner solar system planetesimals. And if you look over here, they sample 1, 2, 3, and they sample seven different planetesimals over here. So what we see over here is that the nitrogen isotopic composition, the variation of the nitrogen isotopic composition in the inner solar system planetesimals is actually much larger than that of ancestite chondrites. And if these planetesimals, if an aggregation of these planetesimals are the primary building blocks of Earth, what this means is, to recreate the nitrogen isotopic composition of the Earth's mantle, you need some contribution of the from outer solar system materials. So what this means is that contribution of 15 enriched materials, probably from the outer solar system, is necessary to explain the nitrogen isotopic composition of the Earth's mantle. You cannot explain the nitrogen isotopic composition of the Earth's mantle solely by accreting inner solar system materials. You need some materials from the outer solar system. So hopefully in this second part of the talk, I have convinced you that combining meteorite data with high pressure temperature experiments can give us many new insights related to the origin of volatiles in the rocky planets, including Earth. So now I'll move to the last part of the talk, where I ask this particular question: can iron meteorites help us explain the unique volatile depletion pattern in the Earth? Again, if we look at the volatile abundances in the bulk silicate Earth, carbon, nitrogen, and hydrogen are depleted by 2 to 3 orders of magnitude in the bulk silicate Earth relative to primitive chondrites. Over here, I'm going to focus on carbon and nitrogen together, because carbon and nitrogen are present together. They are present in similar carriers in the primitive materials in the early solar system. So over here, if you see, I have represented 2 different estimates for carbon. The higher estimate is by Bernard Marty, and the lower estimate of the carbon in the bulk silicate Earth is by Mark Hirschman. So I'll use both of those estimates. And now in the last part of this talk, I'll use carbon by nitrogen ratio as a proxy now to track the origin of volatiles in the bulk silicate Earth and track the reason behind the volatile depletion pattern of the bulk silicate Earth. So if you look at the carbon by nitrogen ratio in the bulk silicate Earth by these 2 different estimates, remember the bulk silicate Earth is everything in the Earth except the Earth's core. So if you look at the carbon by nitrogen ratio on the bulk silicate Earth is higher relative to that of different classes of chondrites. So what this is what we call a superchondritic C by N ratio of the bulk silicate Earth. And this has been a very important problem, that how do you explain the superchondritic C by N ratio of the bulk silicate Earth? People have worked extensively on this problem over the last 10 years. So the way this question has been asked is that you initially accrete materials with chondritic C by N ratios, then how do you create a superchondritic C by N ratio on the bulk silicate Earth? Earlier people thought was, if you preferentially put more nitrogen into the core relative to carbon, so if more nitrogen goes into the core relative to carbon, then the residual bulk silicate Earth should have a superchondritic or a higher C by N ratio. But when people did experiments, high pressure temperature experiments, they found out that nitrogen is actually not more siderophile than carbon. Nitrogen does not preferentially go into the core relative to carbon. So this solution does not work. The other possible solution was that during magma ocean degassing, you can actually put more nitrogen into the atmosphere. And if you ablate those atmospheres during impacts, so if the atmospheres are gone and atmospheres are nitrogen rich, then the residual bulk silicate Earth should have a superchondritic C by N ratio. But when we know that nitrogen and argon have similar degassing efficiencies from magma oceans, so if you are removing nitrogen, you are removing argon as well. So if that is true, then the bulk silicate Earth should have a chondritic C by N ratio. But if you look at the nitrogen by argon in the bulk silicate Earth, it is actually a subchondritic ratio. So this solution does not work. So then people have come up with many fancy solutions, including me, to explain this particular problem. So when I started working in this on my postdoc with Paul Asimov, we said, okay, let's test the inherent assumption over here. That is, are the materials that are making up the bulk silicate earth, do they actually have a quadratic C/N ratio? And to answer this problem, we'll again go to a certain class of meteorites known as iron meteorites, because remember, iron meteorites sample the earliest form planetesimals in the early solar system. So what we thought about over here was, can we use iron meteorites to explain the superquadratic C/N ratio of the bulk silicate earth? The problem we thought was relatively simple. We know from meteorite data the carbon and nitrogen contents of the cores, and we thought, okay, experimentally, we know how nitrogen and carbon partition between metals and silicate mills. So you know the carbon content and nitrogen content in the core. We know how they partition between metal and silicate mills. So through that, you can reconstruct the carbon and nitrogen contents of the bulk planetesimals. Once you know that, then you know the C/N ratios of the bulk planetesimals. But when we started working on this problem, we realized that the problem is actually much more complicated. And the reason behind this is that iron meteorites do not actually sample the entire fractional crystallization sequence of the core. So what I mean over here is that when you form a metallic core, then the core slowly starts to crystallize. I don't care over here whether the core crystallizes inside outwards or outside inwards, but the core slowly starts to crystallize. And before the core fully crystallizes, we know from planet formation models that the planetesimals got disrupted. And the iron meteorites are only sampling the solid regions of the core. We are not sampling the liquid regions of the core before this disruption. So we only have partial records of the volatile inventories of the cores. We do not sample the entire cores over here. And if the evidence is clear, well and clear, if you look at group 2C, we only sample the first 30% of the fractional crystallization sequence. That is, 70% of the core is missing in our meteoritic record. For group 2D, we sample the 80% of the fractional crystallization sequence. The story over here is, for different groups, we sample different stages of fractional crystallization sequence. We do not sample the entire core. And why is this number important? Why is it very important to sample the entire core? If we look at the composition, the reconstructed composition of the parent cores, they're primarily made up of iron and nickel, but they also contain a very important non-metal in them in very large quantities, and that element is sulfur. And what happens with sulfur is that sulfur does not go into the solid metal during fractional crystallization sequence. For example, if you start with a core that contains, the parent core contains 10 weight % sulfur, and you slowly start to solidify the core. When 50% of fractional crystallization sequence is done, the solid core will contain 0 weight % sulfur, and the liquid will contain 20 weight % sulfur. So basically, the unsampled regions of the cores are actually much more sulfur rich relative to the sampled regions of the cores, which are sulfur free. We do not sample any sulfur rich regions of the cores. So what we needed over here was, we needed to experimentally determine how carbon and nitrogen partition between solid and liquid metal. Again, the story is simple. We know the amount of carbon and nitrogen in the sample regions of the cores or the solid regions of the cores. If we can experimentally determine carbon and nitrogen partitioning between solid and liquid metal for a given sulfur content in this liquid in this liquid metal, we can actually reconstruct the carbon and nitrogen inventory of the entire core. So to do this, we now did different stages of different set of experiments, and these are fractional crystallization experiments. And in these experiments, we do not have metallic and silicate metals, because only we are reconstructing fractional crystallization of the core. So the partitioning over here is between solid and liquid metal. So in this is a typical experimental product. You have solid metal over here, you have liquid metal over here. And we did these experiments in a way that you reconstruct the nitrogen and carbon partitioning as a function of sulfur content of the liquid metal. So over here, this partition coefficient represents nitrogen content in the solid divided by nitrogen content in the liquid, and same is for carbon. Concentration in the solid divided by concentration in the liquid. So if you look at the experimentally determined numbers here, what do we see? We see that nitrogen and carbon are incompatible elements when the the equilibrating core has less amount of sulfur. But as the fractional crystallization sequence proceeds, the liquid metals, these equilibrating liquid metals, the core should be very sulfur rich. And in those cases, nitrogen and carbon are actually become much more compatible. So what this means over here is that if we end the fractional, if you're only sampling the fractional crystallization sequence up till here, for example, then the solid metal should contain much more nitrogen and carbon relative to the liquid metal. So we are sampling the nitrogen and carbon rich regions of the core, and the nitrogen and carbon poor regions of the cores are actually missing. So what we did now is we know the nitrogen and carbon contents in the sample part of the cores, and we use these partition coefficients to actually constrain the nitrogen and carbon contents in the sulfur rich unsampled parts of the cores. So what we found out over here was that the carbon contents in the unsampled parts of the cores are very similar to that of the carbon contents in the sample parts of the core. And this should be very clear because in these set of conditions, the carbon partitioning between solid and liquid metal is approximately 1. So for carbon, it does not make a lot of difference. But if we look at nitrogen contents of the missing regions of the cores, we see that the sampled regions of the cores are actually much more nitrogen rich than the unsampled regions of the cores, because the unsampled regions of the cores are very sulfur rich, and they should not contain a lot of nitrogen. So basically now we have nitrogen and carbon contents in both the unsampled and the sampled regions of the cores, and then we use that to reconstruct the carbon and nitrogen inventory of the entire cores. And from our previous studies, we know how nitrogen and carbon fractionate between solid and liquid metal. So finally, we can now constrain the carbon and nitrogen contents of the entire planetesimals. So if you look at the carbon and nitrogen contents of the chondrite parent body, of the iron meteorite parent bodies over here, this is the bulk planetesimal over here. These are these empty symbols over here. And this is where chondrites lie, and this is where the bulk silicate earth lies over here. The first thing that we'll notice in this plot is that the carbon and nitrogen inventories of the iron meteorite parent bodies is actually much lower than that of chondrite parent, or much lower than that of chondrites. So what this means over here is that when you start to heat up a planetesimal, before the interior of the planetesimal undergoes large-scale melting, it should undergo thermal metamorphism. And during this thermal metamorphism, all these nitrogen and carbon-rich organic phases would start to decompose and these fluid phases should freely percolate out because the porosity and the permeability of the planetesimals is very high. So basically what you do is you lose a lot of nitrogen and carbon from the interior of the planetesimal before it gets locked, before core mental differentiation happens. You lose a lot of nitrogen and carbon inventory. So basically this answers a very important question. So this kind of tells us is that the thermal metamorphism of planetesimal is actually the primary cause behind the volatile depletion of rocky planets and planets, because during this process, most of the volatile loss takes place. That's why the final rocky planets are volatile depleted, because you've lost all of that nitrogen and carbon inventory during thermal metamorphism. Now, if we start to compare the C/N ratios of these meteorites, so these are the C/N ratios of chondrites. This is the C/N ratio of the bulk silicate earth. So if you see that the volatile rich iron meteorite parent bodies, their C/N ratio is actually very similar to that of the bulk silicate earth. And the C/N ratio of the volatile depleted iron meteorite parent bodies is actually lower. Now the question arises, are these planetesimals with higher C/N ratios are more representative of the basic building blocks of rocky planets like Earth? So what we know from a lot of iron meteorite literature, we know that most of these cores underwent disruption before the cores got fully crystallized. And there is evidence from metallographic cooling rates and palladium-silver isotopic systematics that all these volatile depleted iron meteorites, their cores actually underwent degassing after the disruption of these planetesimals. So what this means is if the cores underwent degassing after the disruption of these planetesimals, they lose a lot of nitrogen and carbon during the secondary degassing event, which means that the actual nitrogen and carbon inventories of even these parent bodies, their actual parent bodies before disruption, would actually have been very similar to these. So what this means over here is that the C/N ratios of these iron meteorite parent bodies, because they're recrystallized cores, their C/N ratios are not representative of the building blocks of rocky planets. Or indirectly, the C/N ratios of iron meteorite, of volatile rich iron meteorites, they are representative of the building blocks of rocky planets. And as you can clearly see, the C/N ratios of these iron meteorite parent bodies are very similar to that of the bulk silicate Earth, which simply means that the superchondritic C/N ratio of the bulk silicate Earth would actually be a natural consequence of Earth's accretion, that the differentiated planetesimals that made up of rocky planets, they have superchondritic C/N ratios. Also, it means that the other rocky planets like Venus and Mars should also have superchondritic C/N ratios. So with this, I'll come back to the 3 key take-home messages from this particular talk. So the first thing that you need to remember from this particular talk is that as has been postulated for decades, chondrites may not actually capture the bulk volatile inventories of the earliest form planetesimals in the early solar system. So, and as I showed you, iron meteorites are a much better proxy. The second important point is that the nitrogen inventory of the Earth's mantle contains components from both inner and outer solar system reservoir. And thirdly, the superchondritic C/N ratio of the bulk silicate Earth can be a natural consequence of Earth's accretion, because the planetesimals that made up the Earth, the iron meteorite parent bodies, they likely had superchondritic C/N ratios. So I'll just have a small announcement that I'm starting as an assistant professor in the School of Molecular Sciences and School of Earth and Space Exploration in Arizona State University. And we got funded for like a national facility. So that facility is going to be called FORCE, and we're building the biggest high pressure temperature facility in the entire US. It's probably going to be one of the biggest high pressure temperature facilities in the US, and I'm going to lead the research program for that particular facility. And I'm looking for hiring highly motivated students and postdocs who would be very interested in using high pressure temperature experiments to solve problems related to cosmochemistry, planetary science, and exoplanetary sciences. We are going to have state-of-the-art instruments, very special multi-anvils, like a dia press and the 6,000-ton uniaxial press that can recreate pressures up to 50 GPa. We are going to have internally heated pressure vessels to recreate planet differentiation conditions in small planetesimals and recreate magma ocean degassing, so on and so forth. So if any of you might be interested, just drop me an email. I'll be happy to talk to you guys. And with this, I'll leave the 3 key take-home messages, and I'm happy to take any questions if there are any. Thank you.
Okay, great. Thank you very much, Daman. That's the time for questions from our participants. So if you have any questions, feel free to open your mic, or you could leave your question in the chat, and I could read your question on your behalf. So any questions from our participants today? Okay, let me start with some questions while others are preparing. So actually, I have separate questions. Come with the first one in sulfur. So according to your first take-home message, so that means that the contrast, if my interpretation is correct, that is the contrast sulfur composition is less than the accreted chondrite sulfur concentration. Because since the
carbon,
other core is
the carbon and nitrogen, not sulfur.
And the sulfur.
No, carbon and nitrogen, because the thing about carbon and the thing about sulfur is not lost during thermal metamorphism, because sulfur is mostly in the form of sulfides. Mm-hmm. So even if you heat up a planetesimal, you're not going to lose a lot of sulfur. But the thing about carbon, and nitrogen is it's mostly in the form of organics. So they are these macromolecular organics, and some of them are very thermally unstable. So most of the organics start to decompose at very, very low temperatures, at temperatures around 200 to 300 degrees C. So basically, and people have looked at these the combustion profiles of chondrites when they look at carbon and nitrogen. They indeed see that you lose most of the nitrogen and carbon at very low temperatures. So when you start to heat up a planetesimal, the chondrites start to decompose, and the planetesimal has not compacted. The porosity and permeability is very high. So you recreate this carbon and nitrogen bearing fluids, and of course, ice would start to melt, and you start to freely percolate these fluids out of the planetesimal before the planetesimal sinters and locks down. You won't lose sulfur during this process is because sulfur is primarily in the form of in more refractory phases as sulfides. And if you look at the iron meteorite cores, they actually contain a lot of sulfur. They contain up to 20 to 25% sulfur. So you're not losing sulfur, but you're losing a lot of carbon and nitrogen. So it's very tricky when people combine the accretion history of carbon and nitrogen with sulfur, because carbon and nitrogen are highly volatile elements. Their carriers are very different relative to sulfur. Sulfur is a moderately volatile element. So it's not a good idea to actually couple carbon and sulfur together when you're trying to recreate the accretion history of highly volatile elements. They behave very differently during planetesimal differentiation processes, and their carriers are completely different.
Okay. Then another question relative to nitrogen. So that in my understanding that for the surface process, such as lightning, or in the earlier Earth process where they at a time when, for example, the Earth magnetic field was not developed as what it is today, the solar wind that could ionize the atmosphere and then could produce a lot of different nitrogen species that could potentially fractionate nitrogen isotopes. So from your perspective, that how does this affect the system that you're working on?
Yeah. But I think what I'm basically interested in, okay, like those processes could have been very important, but what we take over here is, okay, take the present day bulk the nitrogen inventory of the atmosphere. We look at the present day bulk volatile, the isotopic signature of nitrogen in the Earth's atmosphere and the bulk silicators. We take all of that together, the aggregate, whatever has been effective, whatever processes, take the present day inventory and compare it to the primitive building blocks and try to say, use it as a comparison. So there might have been processes that might have affected them, but in the end, we are sampling all of that right now, right? Like we have all that until and unless we lost that nitrogen, we lost that reservoir itself. But if we sample that reservoir right now, it doesn't matter whether it got affected by other processes, as long we take it into account when we calculate the nitrogen isotopic signature of the bulk silicate Earth.
Okay. Any more questions? Other questions from our participants? Sorry, I took some time. Another question based on your second last slide is your advertisement. So for the large operators that are at ASU, for the pressures that are going to be about 40, 50 GPAs. So are you going to use synthesized diamonds for the cubes?
What is it?
Where people use synthesized diamonds as the cubes for the large
we might
for
do
the
it
40, 50.
Yeah, we haven't discussed the strategies as of now, so we're gonna start calibrating those machines. So we're still in the process of purchasing them. I think one of them, this large press, this press is already delivered. I think it's gonna be installed in by the end of this year. And the other one, which will go to very high pressure, is this diatype press. We'll think about the calibrations at a later stage. We haven't started working on those aspects right now, but we're going to have a multitude of facilities. We're going to have piston cylinders. We're going to have these large presses. We're going to have internally heated pressure vessel, gas mixing furnaces. So the idea is to do all different aspects of planetary and exoplanetary science and just under one roof at this point of time. And I think these are very unique instruments, and I think so just trying to develop this whole national facility to do this kind of stuff in the US right now.
Okay, I think with that, we can finish our webinar today. So thanks everyone for your participation, and thanks our speaker again for the talk. And our next webinar, well, we'll be announced later in our schedule. Okay, have a great day, everyone. We can stop recording now. Bye-bye.